everybody, Dr. Hayden here. So this video is the first part of a series of videos focused completely on thermodynamics. In this video, we're going to introduce the concept of thermodynamics and contextualize why we care about thermodynamics. And then in the following videos, we're going to focus on enthalpy, entropy, how we calculate the change in Gibbs free energy, as well as some calorimetry. So again, in this video, we are asking ourselves, what is thermodynamics and why should we care? Throughout this video, we will also define the terms endergonic and exergonic, teach you how to analyze an energy reaction diagram in order to predict whether a reaction is spontaneous or not. We will also compare and contrast the concepts of thermodynamics and kinetics, as well as define the term energy of activation. All right, so let's get started. So thermodynamics is the study of how energy flows from system to system or from the system to the surroundings. In chemistry, we can use thermodynamics to help us predict whether or not a reaction is spontaneous or not based on how that energy is flowing. When we talk about that thermodynamics, however, we must keep in mind two rules. Rule number one, energy cannot be created nor destroyed. It can only change forms or pass from system to system or system to surroundings or surroundings to system. So again, energy can only change forms or flow. This is actually how we can harness energy from the flow of water to convert it to electricity using dams. Rule number two, a system is constantly seeking greater disorder. By increasing its disorder, it can lower its energy potential. So systems are always looking to decrease their potential energy. Often in chemistry, when we talk about thermodynamics, we talk about the concept of a change in free energy, or the energy of the reactant changing as we make product. We can also call this the Gibbs free energy, and it's often designated as delta G. Now, you'll see two different forms of delta G as you continue in your learning or understanding of chemistry. You'll see delta G, and you'll also see delta G naught. Delta G naught is referred to as our standard Gibbs free energy. This talks about the free energy of a system in equilibrium. Delta G, however, is just the Gibbs free energy, typically of a system that is not in equilibrium. So we have perturbed the system by changing the concentration of our reactants or our products. This is very important to keep in mind as you continue through this module. Most of the videos in this module are going to be focusing on delta G naught. Okay. So now that we've sort of broadly discussed the term thermodynamics and determined why chemists care, again, it allows us to determine whether a reaction, such as A plus B yields C plus D, is going to be spontaneous or not. So remember, the Gibbs free energy, or the free energy, tells us the potential energy of a substance. And when a substance at a certain potential energy reacts to form products, we often have a change in that potential energy. When that change happens, energy is either released into the system from the reaction or absorbed from the surroundings into the reaction in order to drive that reaction forward. This is what we call our change in free energy, and we can follow that change in that potential energy, again, to determine whether or not a reaction is spontaneous or not. So for example, let's say we have a reaction A plus B yields C plus D. If the potential energy of our reactants, A plus B, is higher in energy than our products, C plus D, then we are going to have a drop in the free energy of our system. When we have a drop, we say we are releasing energy from the system into the surroundings, and we get a negative change in our delta G. That negative change, again, indicates that energy is released from the system, our reaction, into the surroundings. And we call these types of reactions exergonic because energy exited the system. Exergonic reactions are then by nature spontaneous. Remember, rule number 2 states that systems are always looking to lower their potential energy. So if we go from a higher energy state to a lower energy state, and we release energy from the system into the surroundings, then we have a spontaneous reaction. Spontaneous reactions mean that they will occur in the forward direction as written without help from any external influences. They're spontaneous, they'll occur on their own. However, if instead our reactants are lower in potential energy than our products, then we will have an increase in our delta G, meaning energy was brought into the system from the surroundings. These type of reactions are called endergonic, meaning energy went into the system in order to help drive the reaction forward. Now, because we are bringing energy in and we're going from a lower potential energy state to a higher potential energy state, endergonic reactions are non-spontaneous, meaning they will not occur favorably in the direction that they are written without help. Now, chemists can help spur endergonic reactions to be exergonic and drive them forward by messing around with the parameters of the reaction. We can play around with temperature, volume, pressure, as well as the relative concentrations of our reactants compared to the concentrations of our products. So remember, when we're talking about the Gibbs free energy, we often refer to our standard Gibbs free energy, which is the energy of a reaction at equilibrium. If we perturb the system by changing the relative concentrations, we now push our system out of equilibrium, and we can now talk about the Gibbs free energy under different conditions, and we can change the potential energy of the system to make it exergonic. This is all due to Le Chatelier's principle. Remember what Le Chatelier's principle said? A system that is in equilibrium will shift in response to a stress. So if we increase our reactant concentrations high enough and keep our product concentrations low, we can force the reaction into the forward direction, making a non-spontaneous reaction spontaneous under those conditions. Okay, so you now may be asking yourselves, well, what happens if the potential energy of your reactants is the same as the potential energy of your products, where A plus B is at the same level as C plus D? Well, this is a special circumstance, right? Here, you're going to get a delta G change of 0. This happens at a system in equilibrium when your equilibrium constant is equal to 1. And basically what this means is that the reaction is just as likely to occur in either direction, meaning it's spontaneous in either direction. Now, as chemists, we can kind of force it in which direction we want, whether we want the forward direction or the reverse, again, by playing around with those experimental parameters of temperature, pressure, volume, and the concentration of our species within the system. So while thermodynamics can tell us whether or not a reaction will occur spontaneously or is favorable in one direction or the other, it cannot tell us how quickly a reaction will occur. That is governed by kinetics. So for example, let's take an example look at the combustion of wood. Right? So all combustion reactions we know are highly favorable. We know that because what happens when you burn fuel? you get heat, right? That heat release tells us that energy is leaving the system and going into the surroundings. That's a great clue that will tell you that the reaction is exergonic, meaning energy is exiting. We are lowering the potential energy of our reactants to our products. However, the one thing you notice is that when you go for a walk in the woods, trees aren't just spontaneously combusting all around you, right? We know if we take wood and add oxygen, it will combust to form CO2 and H2O. The reason it doesn't do that is because it takes a spark, and that spark can come from a lightning strike or a match, either in a controlled way, hopefully, or a uncontrolled way, which sometimes happens in forest fires. Now, that spark gives us enough energy to reach what we call our energy of activation. So most reactions have to go through this energy of activation before they can drop down to their more favorable products. That energy of activation basically is the amount of energy required for the reactants to come together at the right time in the right place in order to react. And that coming together usually requires an increase in the potential energy in order to form something we call our transition state. And then once we formed our transition state, we can drop very quickly to form our products. Now, the one thing that doesn't change is the relative difference in the energy between our products and our reactants. That still stays the same. So our overall delta G is still going to be negative, and it's still the same value. However, depending on how high this energy of activation is, whether it's larger or smaller, can help us control the rate at which that reaction occurs, right? So an energy of activation that is very large may take a reaction much longer to react in order to generate their products than an energy of activation that's smaller. And as chemists, we can actually do things to the system to help drop that energy of activation. But that's a different lecture. So again, in this video, we were discussing what is thermodynamics, why do we care about thermodynamics, and how can we use the change in Gibbs free energy in order to predict whether or not a reaction is spontaneous or not, and how does kinetics play a role in all of this. Again, if you are struggling with any of the concepts in these videos, please reach out to your instructor, a TA, a peer, somebody. Don't struggle alone. Thanks, and have a great day.